So let's take an example. Let's say helium atom. Helium atom has 2 electrons in one space orbital. We normally call it 1s, but now we have to be careful because whatever I am calling 1s has to be obtained by Hartree-Fock. I have already told you that part I have skipped. How do I get phi? I have skipped. But let's call it 1s, whatever I get. And this is a common chemist notation. Whatever hydrogen atom orbital, they call it the same name. But this 1s is actually a complete misnomer. This is 1s for the helium atom. This is different from 1s for the hydrogen atom, but let's call it 1s, doesn't matter. Or I can call it phi 1. I think that is safer. So my determinant is now phi 1 alpha, phi 1 beta, right? Note again, whenever you write determinant, and this is a golden rule, you must write in terms of spin orbitals. You can never write determinant with only space orbitals. I am writing the form of energy in terms of space orbitals. But determinant cannot be written in terms of space orbital. Without spin, the antisymmetry has no meaning. So I must specifically write phi 1 alpha, phi 1 beta. Okay? Then I am going to use, this is a closed shell by my definition. You have 2 spin orbitals, 1 alpha spin orbital, 1 beta spin orbital, and the space parts are identical, phi 1. So it's by my definition of 1, 2, 3, it's a closed shell. Is it clear? Of course, all this you know already, but I am just putting it in the very rigorous perspective now. So now I want to calculate psi h psi. Apply, do the spin integration directly. I have the form. To simplify, let me also call phi h phi I as h I. So that some of the notations will get simplified. So then what is the result? Result is 2 times H11, right? Because phi 1, H phi 1, you have 2 electrons, so it will become 2 spin orbitals, so it will become 2 times H11. There is no other further summation because there is only one special orbital. Then let me write down the rest of the parts. So when I equal to 1, I is only 1, so you have a J11 of course. And this part is silent because you have only 1 orbital, right? So there cannot be I not equal to J, it has no meaning because there is no 1 and 2 here. In terms of space orbital, remember, these are in terms of space orbital, I have only 1 space orbital, that's the result. Because if I would have applied here also it is same, I would be equal to 1, J would be equal to 1, 2 JII minus KII is JII, because JII is equal to KII. Remember this form. Alright, so very easy. I have a 2 electrons, each of them their 1 electron energy multiplied by 2 and 1 Coulomb interaction between 2 parallel spins. Note that there is no exchange interaction here. Don't forget, there is no minus K11. Actually there is a K11, but unfortunately one of these J has cancelled it. Okay, so there is no exchange here, there is only Coulomb. Finally what survives is only 1 Coulomb interaction. And note, I am going to come back to this. Let us take another determinant, phi 1 alpha, phi 1 beta, phi 2 alpha, phi 2 beta. So this could be helium atom. Hey, this could be beryllium atom, right? 4 electrons. This could be beryllium atom. So phi 1 is 1s, phi 2 is so-called 2s. Whatever it is, this is not again hydrogenic 1s and 2s. We will find that out. But given a phi 1, phi 2, you can now apply the same form. So what will be the energy? 2H11, right? Plus 2H22. That's the first thing. Then I apply this. I have a Coulomb J11 plus J22. That's clear. Now you have I not equal to J. There is a J12. So it can be 1, 2 or 2, 1. So it will become 2J12 minus K12. But now I can be 2, J can be 1. I have not done that symmetry. So I have to write it once more. Plus 2j, 2, 1, which is same as 1, 2, minus k1. Because I did not use I less than j. If I would have used I less than j, this should have been multiplied by factor 2, which I didn't do, but you can do it here. So you have 4j12 minus k12, and so on. So let me analyze this. How do you get this 4 and 2? So that's important. And this is where a good physics will come. So let me write down this beryllium. 2 electrons here in your notations. So this is phi 1, this is phi 2. Again, this is so-called 1s and this is a 2s orbitals. So what are we doing here? We are first taking for each electron its own kinetic and 1 electron attraction, which is H11, H11, H22, H22. So that part is cleaned up. Then for each of the orbitals, the 2 electrons sitting has only Coulomb interaction with anti-parallel spin. If you notice further, I have 4 pairs of J12. How does it come? There are 4 pairs of anti-parallel spins, one sitting in 1, one sitting on 2. 4. This, right? So I have got up and down, and here also I have got up and down. So total number would be 6. And there are 2 pairs of parallel spins. Up, up, down, down. So that gives you 2 times k1. So one very important physics you get here, that without looking at it, you can actually say that parallel spins have only have exchange interactions plus Coulomb interactions. So that is how your 4j12 comes. 4j12 came because this has a Coulomb interaction with this as well as this. This has a Coulomb interaction with this as well as this. So everything has a Coulomb interactions. Anti-parallel spins like 1, 1 here or 1, 2 have only Coulomb interactions. Yeah, so eventually the final outcome is that if you have anti-parallel spins, they have same space orbital, yes. Other possibility means? Yes. Correct, correct. Because JII is same as KII. If I not equal to J. If I equal to J, it cannot be both are. Well, whichever way you interpret. That is a Pauli principle also in a way, that you cannot have 2 up spin. The point that I am trying to say, anti-parallel spins have no exchange. That is the important thing. Okay, so anti-parallel spins have only Coulomb. Parallel spins have both Coulomb and exchange. That is important. So if we have to count Coulomb, count both parallel and anti-parallel. If you want to count exchange, count only parallel spins. So now you look at it. There are how many pairs of electrons are there total? 4 electrons. How many pairs are there? Don't have to worry about who are in which orbital. 6 pairs. 4c2, right? 2 of them are here and 4 of them are like this. All the 6, there should be 6 pairs of Coulomb. And you see there are 6 pairs of Coulomb. 1, 2 and 4. So the 6 Coulomb is divided into J11, J22 and 4J12 because each pair has Coulomb. However, only a parallel pair has exchange. So now you have only 2K12. Correct? So in a way, the Coulomb, so the other way of writing this is Coulomb is for all pairs. Note that when I am saying this, this is in terms of the space orbitals, J and K, after the spin integration. So Coulomb is for all pair, exchange is for only parallel pair. Okay, when I say up, up, it could be down, down, parallel or anti-parallel. That's all. So count out the number of parallel pairs, number of all other pairs. So this is parallel pair is 2. Again, when I say parallel, it means either both of them alpha, both of them beta. Both they should be same spin basically. So that is what I mean by parallel. So it's very easy. So I give you any determinant, you should be able to write down in terms of Coulomb and exchange. In fact, what turns out later, and this is something that I derive for closed shell, that this result is fairly general result for all determinants. The spin integration I perform only for closed shell, okay, starting from the Slater's rule. The Slater rule is valid for any determinant, any one single determinant. And if I do the spin integration, this result that I got is a fairly general result. So let's assume that I give you some open shell now, a very high spin state, phi 1, phi 2, phi 3, each of them are up. So it's a quartet state, okay. So it's a high spin state. So what will happen here? Phi 1, phi 2, phi 3. Don't worry about ground or excited state, doesn't matter, it's a determinant. So your energy will be H11 plus H22 plus H33, correct? What will remain now? They are all parallel, so everything will remain. So I will have J12, J13, J23 minus K12, minus K13, minus K23. Everything will remain, because all pairs are now parallel pairs. So Coulomb doesn't get anything extra. This is not a closed shell, but I told you that this result is a fairly general result. So even if I did not do the spin integration for open shell, but even if I start from an open shell determinant and do the spin integration, in terms of space orbitals, it turns out that you get the same result. So I am not going to derive it, it can be easily done. I am actually showing the outcome of the result, okay. So let's assume that I change one of the electrons. I make this like this now. So same 3 electrons, put in 2 orbitals. So it's a lithium atom ground state, doublet. I will have now H11 twice, because 2 electrons are in H11. H33 will vanish, of course, because there is no 3 now in the occupied. 2H11 plus H22. And now I can rewrite the Coulomb in the exchange. All pairs will have Coulomb. That's the first important thing. All pairs will have Coulomb. So I have how many pairs now? 3C2, 3 pairs. That's very clear. There has to be 3 exchange. So one of them is J11 and 1, 2 is 2 J12, correct? And 1 parallel minus K12, that's it. Actually, once you understand this rule, simply by inspection of the determinant, you should be able to write the energy. So that is what I am teaching you. You don't have to go through the spin integration. I did the spin integration for closed shell, and then I just declare that the result that I get in terms of the Coulomb and exchange for parallel and anti-parallel spin is a general result that you get for every determinant. Okay, so now what I am going to do is to simply apply that result and write down fairly straightforward, in a fairly straightforward manner. Is it clear? Let's take another very good example, which is what many of you use in inorganic chemistry and so on. So let's say there are 2 orbitals, 1 and 2, which are degenerate. Okay, and I have 2 electrons. So there are different ways of putting it. Let's put it this. I am only going to analyze 2 cases. One is this, another is this. I could have put 2 electrons also in one, doesn't matter. That's easier case. What will be the energy in each case? I'll just write down the energy quickly. J11 plus J12, sorry, H11 plus H12 H22, yes, H11 plus H22, then you have a J12 and that's it, right? Let's write it down here. Again here 1 and 2, H11 plus H22 plus J12 minus K12. Now it's very important. because you not only have one pair, but that's also a parallel pair. So parallel spins have both exchange and Coulomb. Anti-parallel spins have only a Coulomb. Now, it is very important to note that each of these exchange integrals and Coulomb integrals, if I integrate actually in terms of special orbital, they are always positive. The values are always positive, again without proof we are stating. So, K is a positive quantity. So, which will have a lower energy? The second one. And that is essentially the Hund's rule. What does the Hund's rule say? If you have a degenerate orbitals, the electrons go parallel. That's a proof of this actually. So, I can take anti-parallel, do the spin integration. This result will come from the spin integration, as I told you. It's a fairly general result. I didn't do the spin integration for open shell, but fairly general result. So, this energy will be greater than this energy, which is a statement of the Hund's rule. So, remember, Hund's rule is a consequence of antisymmetry. Because of the antisymmetry, I am getting the Coulomb and the exchange. Many people feel that the Hund's rule is a very important rule, is a fundamental rule. No, the fundamental rule is antisymmetry. Once I have a Slater determinant, write the Slater rule for the energy, do the spin integration, this is the outcome. And hence the Hund's rule. I ask many people, why does it happen? They will say Hund's rule. I remember, why is Hund's rule? That's what I am asking you. They don't tell exchange. They don't tell this. If you understand that there is a parallel spin, which is exchange, and this is what is called exchange stabilization. Many times you have heard this term. The exchange is stabilizing. So, the Hund's rule is actually a consequence of the Slater rules for the matrix element, which basically comes from the antisymmetric determinant. So, it is basically a consequence of determinant or antisymmetry. Antisymmetry is of course a very high rule. That is the first important rule. You can do anything, energy, you can't break antisymmetry. Symmetry is the most fundamental rule. You can't choose a symmetric wave function for electrons. That's not allowed. Within that, I find that the Hund's rule applies. Okay? Alright, so the point is that this is a very important concept, physical insight that you get from the spin integration, the energies and so on. In fact, this is also something that is done in the inorganic chemistry. If you remember, T2G and EG levels get split and you call it 10 delta, etc. If this is very, very small, it is essentially becoming like a degenerate. And if it becomes degenerate, then the spins tend to align parallel. And that is the origin of the high spin complexes in inorganic. You have already done it. If this is very, very high, then of course, they will become anti-parallels, because for example, if this is very high, then obviously this is no longer good. I should do this probably 1 and 2, as well as this. Note that in the same system, I will have H11 plus H22, I will have H11 plus H22, and this of course, if you do this, this will have a J minus K, this will have only J, so this is good. But on the other hand, if I put this guy on 1, then what will happen? This will have H11 plus H22, this will have 2 H11. Each of the H11 is much less than H22, so I have a lot of energy saving here. Although I am losing the exchange, this gap is helping me. And that is the reason helium atom in ground state is not 1s1, 2s1. Because you may ask the same question, that why do anything become paired? Why does anything become closed shell? It's a good question to ask actually. Because then this term takes over. The 1 electron energy is very high, then it doesn't matter, I can afford to lose. And that is why systems become closed shell, remember. Because closed shell, by actual nature, in terms of exchange, should not be favored anytime. Everything should become parallel. But if this gap is very high, then I am losing. Instead of H11 plus H22, 2H11 is much less. Do you understand? So that is why it becomes low spin complex. So in organic chemistry, we teach this. It is not that strict. Is there a class here? Oh, okay. That USB. I thought this is another class. Is it clear? So this actually in organic chemistry, high spin, low spin complex is also consequence of this. It's not taught in the same manner. So if I do a helium atom, 1s, 2s, under external field, where the 1s, 2s gap is decreased, indeed the ground state of helium atom will become triplet. That is how we get from singlet helium to triplet helium under pressure. Because all you are doing is making 1s and 2s degenerate. Otherwise, there is no reason why it should be 1s square. I mean, whatever is 1s, again, I have not derived the 1s. It will never be 1s square, it should be 1s alpha, 2s alpha, or 1s beta, 2s beta. Just because of the 1 electron energy. The 2s is much high compared to 1s. So I can afford to lose the exchange and gain an 1 electron energy. Okay, it's very important, and that is where a lot of physics can be done. So if I have a non-degenerate system, I can bring them close and make it triplet, make it a high spin, and very interesting physics can be done actually. And people are doing it. Materials under pressure, they behave differently. The spin changes, and everything is because of this. So you have to understand this thing. The problem is, of course, the exchange interaction is small. So obviously, in this case, H22 minus H11, that gap is much larger than the K12. So K12 stabilization does not really help. So that's what happens, and that is the genesis of a low spin and a high spin complex in organic chemistry, which is also basically the same concept. Just again, please understand, only from 2 electrons you can get so much insight. You know, many people say 2 electron mein kya hai, bada bada karo. But all insights are coming from analysis of 2 electrons. If you have the physical insight, you know, the 2 electrons, that really gives you a lot. All right, having said this, we will get to the Hartree Fock. And this is something that we will use it later, because when you do Hartree Fock, we are eventually going to write in terms of a space orbital, as I told you. So this expression, at least for the closed shell, please remember. Okay, we will write it down.